Hey, what's up, guys? Yeah, so today I want to introduce the algebraic geometry topology, and the basic this project is this topic is about the real projective space and its fundamental group. Okay, so I will introduce the real projective space and describe how to compute its fundamental group, and via this so-called Van Kaplan theorem. Okay, and because real projective space is like the mystery in like algebraic geometry, in algebraic topology, and if you learn about like physics and something that you always heard about it, and still some I think it's a little bit difficult. So I want to make my own video and describe the detail, and yeah, basically compute the whole fundamental group, and in the future video I will compute the homology and the cohomology. Okay, and welcome to my YouTube channel. Okay. Okay, so let me just quickly define. So one can define the RPN. This is an n-dimensional real projective space. N-dimensional real projective space defined to be, let's say I take the n+1 dimension real Euclidean space and modulo the vector which is okay, so I should say let's say x1 x2 up to xn+1 is identified with y1 y2 up to yn plus 1 if they are related. So yi is the same as lambda xi for some lambda is non-zero. Okay, so this is a quotient, and in order for this quotient to be well defined, you need to delete. So your Rn+1 need to delete 0. Okay, you need to delete 0 point. Okay, so which is a real projective. So you can imagine that you are in a n+1 dimension, a ball, and you for each vector which is proportional to each other that you identify it. So you remove 0. Okay, and you can use your differential geometry to check that this RPN is a n-dimensional manifold. Okay, and also I want to say that so to be the fully rigorous, we should define a topology on RPN. So this definition is just a set, right? You can view it as a set. So but there is a natural topology Rn+1 quotient up to this and the quotient is, right? So you can just using the quotient topology. Okay, but I guess most of the people do not understand this, so it's fine that if you don't understand what I'm saying, it's fine. Okay. Okay, so let's work in the I will work in the two n equals to 1, n equals to the case, and give you a feeling what the hell is going on. So so if n is equals to 1, that you get RP1, right? So RP1 is just a you can view two-dimensional, and you first delete 0, so you should delete 0, and then you quotient what? You quotient the x1 x2 identify with y1 y2. There's a y1 is lambda x1, y2 is lambda y2, y2 is lambda x2. Okay, so you can view as you're using your lovely picture. So you get a circle, right? And then you identify the antipodal. Okay, so this is the antipodal. So it means that hopefully I didn't spell it wrong. Okay, so the antipodal, right? You identify this point. So you can view this as a circle. You can view this as a semicircle, but these points identified with these 2 points are identified, right? So I draw a solid for this point. So this is what you get. Okay, so this space is RP1. Okay, so you can prove that the theorem, which is I'm going to do this, is RP1 isomorphic to S1. Okay. So this is RP1. Okay, so let me quickly prove it. The proof is almost trivial, right? So since you have the beautiful geometry picture, so let's say you want to construct a homeomorphism from F RP1 to S1. So I guess it's very trivial, right? So because your RP1 is parameterized by theta, or I should say exponential I theta for theta less than 0 and pi. Okay, so you can just create a double map, right? Just do the so you can define f of x to be x squared. Okay, so this guy become a circle, which is exponential I theta, and the theta from 0 to 2 pi, which is a circle. And obviously that you can check this is a 1, 1 on 2 and 1, 1 on 2 and continuous, and its inverse is also continuous. Okay, so very simple. So in this case, that RP1 is just a circle. So how to compute its fundamental group is very trivial, right? Because we know that the RP1 is isomorphic to circle, and the circle has a fundamental group integer. So this you can check out the Allen Hedger or check out my other videos. But basically, this proving idea you can use the so-called covering map. You can take out you can use the exact sequence and however you want, but it's very elementary results. Okay, so giving me RP1, RP1 is also integer. Okay, so this is trivial case. So how about n equals to 2? Okay, so n equals to 2 is sometimes that people will have the different point of view, but let me just describe the two basic picture. Let me just using a black. Okay, so you take out a sphere, right? And by the way, you first starting with R3, and then you model, you delete 0, 0, 0, and you identify the vector, right? So now you can normalize the length to be 1, so you get the sphere, and you identify the antipodal. Okay, so actually RP2 can view as a S2 modulo the antipodal, right? So let's say x identified with minus x. Okay, actually this is not sphere, right? Because your modulo this may not be a sphere. Okay, because it's not like the one-dimensional that you can take a square map. So this guy is a solid. It's a surface. Okay, so this another way is that you can view as a so I can do the same thing. I can take out a hemisphere. Okay, so I get a hemisphere. Now each point is unique, right? Because I already modeled antipodal map, right? So this is unique. But the equilateral is not unique, right? So I can write as the unique open hemisphere plus the equator modulo the antipodal on the equator. Okay, so now these vectors are two-dimensional. Okay, because they are on the antipodal. Right, so these two. Okay. And so third way, which is usually famous, is that you pull out this, you crush this hemisphere, so you get this. Okay, so this is our famous RP2. Is like you get open disk. So each point in the disk is unique. So each point in the disk is unique. Okay, but the boundary, which is a circle, the boundary which is identified with its antipodal. Right? So this is identified with this, and this is identified with this. Okay, so one can write this RP2 in terms of open disk, two-dimensional open disk, union of the boundary. Okay, but the boundary is a guy which you need to map it to its antipodal, right? Okay, so obviously this is RP1, right? So this is RP1 because this is exactly a circle. So actually RP2 is a D2 open disk union with a circle. Okay, so open disk a circle. Or basically this is another RP1. Okay. Okay, so once you have by the way, sometimes if you see some picture that people will write RP2 as this. Somebody give you a sheet and you identify this, right? You identify this. This is exactly the same as this. Just make it to be rectangle, right? So this is identified with the antipodal. And then in the middle is still the every point are distinct. Okay, so it's exactly this picture. Okay, and so compared to the standard is a torus. So torus look like this, and with the Klein bottle, you look like this. Okay, so this is a Klein bottle. This is a torus. Okay, so there are 3 stupid family. Okay. Okay, so now let's compute the fundamental group of RP2. Oh, in order to do this, we need a technique called the Van Cappen theorem. So I will not talking about the proof because the proof is very difficult. Probably not so difficult, but it takes some time. So let me just skip the proof. But let me just quickly say how to use this Van Cappen theorem. I always has a hard time to remember how to spell this name correctly. Okay. Okay, but the idea is this. So let's say you write your specs X and union with V, union with this V, and that's both are open and their intersection should be non-empty. Okay, so now your pi1 of X will be pi1 U, free product pi1 V, and but free product with the something which is U intersection V. Okay, so what this means that you take the generator. Okay, so there's a different way to do this, right? If you are a category guy, you can call this push out. Okay, but this will make you crazy because you need to think a fundamental group is so-called fundamental group point, and you can use so-called push out. And I will not explain detail. Okay, but this pi1x. I think the computational advantage is that simply speaking, you just take the generator of pi1u and then take the generator of pi1v, and then you do the free product. Okay, so let me just explain. So I think everyone knows about free products. So if I take the G1 free product G2, that I can take the one identity and all the possible G1 or possible G2 and all the possible combination of the string. For example, I can take G1, G2, G. Sorry, maybe I use G free product H. I can get E or G or H or G1, G2, H. This is the same as GH, right? So maybe I can take, let's say I can take GH, HG, and the GHG, and the HGH, and each H and G can be different. So basically, when I write H, I mean some element H, and then you can keep going. Okay, so for example, I think if you take let's say figure 8, which is 8, and you want to calculate its fundamental group, let's say this loop is A, this loop is B, then you get, let's say, you get the free product of Z, free product Z, which is identity, and A or B or AB or BA or ABA or A squared B, so which is infinite and very large. Okay, but modulo this pi1 U intersection V means that you need to take a loop, right? So let's say you can take a generator of U intersection V and then you pull out into pi1 U. Okay, so once you do this, then this will generate some non-trivial zero conditions. Okay, and then you also need to pull this into V. Okay, so this non-trivial condition, at least two guys will give you a constraint. Okay, so this is and you need to model that constraint. This is the Van Cappen theorem, and very abstract. And I will explain the detail when we do the computation. So let's compute this. Okay, so do this. We just very simple thing, right? We take our picture like this, and let's say let me use different colors. Don't worry. Sometimes doing math, sometimes using sometimes pick up like me doing some mathematical video is very difficult. Okay, especially from I'm not Mandarin, so I'm not an English native speaker. So this is U, right? Let's take this is U, and then let's take V. So let's take V to be this. So this is V. Okay. So okay, let's do simple computation. So what's U, right? So U is a disk, right? So U is a disk. So U is just a disk. Okay, so it's trivial. In the topology, open. And then what's V, right? So V is a least guy, right? But you can do the deformation, right? So V is actually the S1. Okay. Okay, so our pi1 U free product with pi1 V will be the S1, right? So we just get pi1 V because this is trivial. So actually we get some loop. We get a loop which is Z2. Which is Z, right? It's generated by, let's say, loop A. Okay, so this is A. Right, this is A. Okay, but what is the U intersection with V? Okay, so U intersection with V will be another circle, which is here. Right, there will be a circle here. Okay, so it's another circle. Okay, so now we can compute we can just do the simple observation to compute the homology. The fundamental group. So we get A, right? We get A, which is we get Z quotient with something, right? Something here, right? And this is generated by A. So we need to see what is A, what is this loop. Pull out in A, okay? Or conversely, let's say I put out A into loop, right? But actually, this A, right? This A in the RP1 language is just a half loop, right? Half loop. Okay. So if you pull this loop into this boundary, right? You get 2A. You get 2A, right? So which you get generated by A, and then you get 2A. Right? But 2A in the loop is 0, right? 2A in the loop is 0 because this guy is trivial, right? So right? Because this is not trivial, right? I mean, this 2A, this A, this how should I say this? So let's not good. Let's do this. So let's say I write this is A. Okay. So this is A, right? And so the fundamental group is generated by something, which should be Z, right? But this A, if you pull out to the boundary, it becomes 2A. Okay. So this means that you need to enforce a condition such that 2A is 0. Okay, 2A is 0. Okay, so your fundamental group should be pi1 should be generated by A, but with the condition that 2A is 0. Okay, so which is Z divided by 2Z, so which is Z2. Okay, so hopefully you understand. Okay, so actually you need to understand all the proof of Van Keppen, right? But the idea is what I'm saying is that you pull out the loop. You pull out the loop generated by U intersection V into the U or V, and then you assume that loop is 0. Then you will generate some additional relation. Okay. So this will give you Z2. Okay. So now let's work in a higher dimension. Okay, so now we can do the simple same thing, right? It's RPN, right? So RPN is defined to be, you can do SN and connect it with the antipodal. Okay. And then this is exactly the same thing that you pull a disk, right? So you do the same thing, right? Because we get RP2, for example, we get RP2 is S2 as identified with this, and then this is just a disk union with S1, right? So simple argument that you can show this guy. You take out you first remove everything and you get hemisphere, hypersphere, and then you crush it. Okay, so you get a DN union with S1, right? So in this case, you get RPN minus 1. Okay. Okay, so now let's assume n greater or equal to 3. And then we need to compute the fundamental group, right? So we get RPN is basically this. Okay, so we can take this as U, this as V, and then their intersection will be something, right? Will be something. Which in a higher dimensional case that you get something, right? So you get Sn minus one. You can think a little bit. You get Sn minus one. Okay, so now let's using backcap. Let me just pull it here, so I can write Rpn is d to the n union with Rpn minus one. So this is X. Sorry, this is U. This is V, and their intersection dn intersection with this Rpn minus one, where isomorphic to Sn minus one. Okay, so you can prove this trivially just using your imagination as previous RP2. Okay, now it's very simple, right? Because I can use the Van Keppen theorem. So Rpn is pi 1 of dn, free product with pi 1 of Rpn minus 1, and pi 1 of Sn minus 1. Okay, but let's assume that n greater or equal to 3, right? So now this pi 1 S2 will not give you anything, right? Because pi 1 of Sn is 0 if n greater or equal to 2. Okay, so you get this guy 0. So you get pi 1 of dn, which is still trivial. So your final results will be pi 1 Rpn is actually the same as pi 1 Rpn minus 1, right? For n greater or equal to 3, which is exactly Z2, right? Because I go back to the 2. Okay, so our final results give you the following. So your pi 1 Rpn, if n is 1, you get a Z2, you get a circle, so which is Z. If n is greater or equal to 2, you get a Z2. Okay, so Z2 means that there are two, right? So there are two different loops, but each loop, if you times 2b, there's a one non-trivial loop, but if you do that non-trivial loop twice, then you get trivial. Okay. So basically, you can try to think the intuition of how this Z2 come from. Okay, so that's it. So yeah, and also in the future that I will describe the Mayer-Victoria sequence and how to use this to compute homology and cohomology of RPA. Okay, so see you guys in the next videos. Oh, by the way, so also one interesting exercise you can check this RP3 is isomorphic to SO3. Okay, so you need to view this as a Lie group. So there are the same as a manifold. Okay, so see you guys next videos.